we've now dealt with 7 different areas of oxyorganic compounds. 6, not counting the amines. In fact, we're just going to leave it at 6 because the amines are found naturally. They're very difficult to produce synthetically in the lab. So we're going to ignore that and let you deal with the reactions used to produce other compounds using amines, which we're not getting to. All we're caring about right now is just a specific reaction for each of the other 6 functional groups and how they are produced. Now we started off with alcohol, so let's do that first. And we did that already, but I'll review real quick as to how to find, so you don't have to go digging back to your videos or your notes from the alcohols. But the way we produce an alcohol is by taking an alkene plus water to produce the alcohol. Now, the thing about the water is that one of the things you learn in organic chemistry is that water is not H2O. It is H2O. I don't mean it that way. But what I mean is that when you think of it as a reactant, you don't think of it as 2 hydrogens and an oxygen. You think of it as a hydrogen and a hydroxide. All right? So this is what we call a binary compound. It splits up into 2 parts: the hydrogen, the positive hydrogen, and the negative OH. Okay? And that's the basis for, in these reactions here, and there'll be other reactions as you get into organic chemistry if you so choose to take it in college, which I imagine quite a number of you will be doing. Now, so let's take an example, do a really easy one which deals with ethene reacting with water. And again, we think of water as HOH, and that's very important. Think of it that way. Now, ethene has this double bond here, and I chose not to draw the Lewis dot structure. You can do it however way you want to do it on your practice problems. But you have a pi bond and a sigma bond. And we talked about that earlier on in the organic section. The pi bond is the weaker of the 2 bonds. And when this collides with it, the bond between the hydrogen and the hydroxide breaks to form an H with an electron and the OH with a free electron ready to rock and roll. Same thing here. When this pi bond breaks, you get electron here, electron here, you got electron here, electron here. And so quickly, because they're in close proximity of each other, they both want to be full, so they're going to latch on. Now, when I first showed you this way back when we did the alcohol section, I said there's 2 possible answers. In this case, now I will draw this out so you can see what I'm talking about. And I'll put the H in there for emphasis. I don't have to because these are all H's, but the OH has to be put in there. This is one product. Now the OH could go in the first carbon, and the H can go in the second carbon. And so you get OH here and H here, and then all of them are H's as well. So my question is here, is this 2 different compounds? Well, the answer is no, because if I take this and spin it 180 degrees that way, I get the same thing. So there is no and here. It's all going to be the same compound, better known as ethanol. But, and there's always that big but. The one we did, and I'm going to do again here, is the propene. And I guess I'll just go ahead and put the H's in there. It's not crazy about it. Plus water, which is hydrogen hydroxide. And again, the pi bond breaks, the electron here, the bond here breaks, electron here, and they form 2 possible compounds. The question is, do you have 2 different compounds? Well, One of them is this. When the H goes here, the OH goes here. I'm not going to put the H there now because it's an H like all the others. And then I'll put the OH there, and the H goes here, and that's what you get. Are these two different compounds? Yes, they are. If you flip this 180 degrees, it comes all the way over here, you don't fit. Flip that, you got the same thing no matter what you do. Two different alcohols. So you have to name them as 2-propanol and 1-propanol. Now, if you're curious, you may ask, oh, you should get about 50-50 mixture of this. Turns out not, but for reasons I can't get into because you won't understand unless I spend like an hour and a half on it. But you will get more of that one than you will of that one. It has to do with stability of a cation. Yeah, that's what I just said. Okay, ethers. We might have talked about this, I don't really remember. I think I may have mentioned it. I don't remember doing one of these, but I'm going to do one now here. In order to synthesize an ether, you take two alcohols that are the same. So, I mean, this is one way. There's a bunch of different ways, and this is for what we call homogeneous ethers, where you have the same thing on both sides of the oxygen. It's a lot simpler to deal. There's something called Williamson synthesis of ethers, where you have like a salt of one oxyorganic compound and something else that you add together, and you get a heterogeneous ether. I didn't want to do that, but you would take two identical alcohols, you mix them together, and you have to have a strong acid. Oh, I forgot to mention that. Yeah, that's kind of important. Alcohols need a strong acid here. We'll put H positive. And again, it's sulfuric acid, like we talked about with the esters. So yeah, strong alcohol, or strong acid. And you get then an ether. So the example I will give you for this is, let's take ethanol, two ethanols. Now, this is kind of like what happened with the esters, where we had an acid-base reaction, and technically, that's what this kind of turns into. Ethers are actually, alcohols are actually not really basic and not really acidic. They're kind of a cross between the two, so they can act like an acid and a base. And the introduction of this hydrogen will force one of them to act like an acid, making the other one act like a base. So it's kind of arbitrary as to which is which. I mean, it's pure randomness. But if I decide to make this the acid, by making the hydrogen remove itself, and that makes this the base because it's working against the acid, then the H and the OH are going to be removed to form water. And water is a byproduct. I should have put up there, but we're just looking at the organic part of this and not the water part of it. But it is a byproduct of this reaction. But then what happens here is that this compound right here comes over here. Now, you've got to be careful when you write these products down. So like, if you write it in this form, it's not too hard to get it wrong, or not too hard to get it right. But if you write it in the CH3CH2OH form, it's a good chance that you may get it wrong. So I would suggest doing it in this form right here. But if you don't, that's fine. But here's the deal. This carbon right here had the OH, so that carbon right there has to go right there. You just kind of turn this 180 degrees and stick it right in there. And there's your ether with 2 carbons each. Now if you do it the other way, use the straight line form of this, you have CH3, CH2O, CH2, CH3. If you write it CH3, CH2, you are now giving that carbon 5 lines, 10 electrons. That can't work. The CH3 is always going to go on the end. The CH2s or the CHs or whatever you have, that's not CH3 goes in the middle. So be careful of that. So there's your ether reaction right there.